We now switch gears a little bit and we're going to talk about something called antiderivatives. So for a large portion of this semester, we've been talking about derivatives. We learned the definition of a derivative, we learned some derivative rules, we learned some applications of derivatives. Now it's time to talk about these antiderivatives. So simple concept here is if I said that the derivative of some function was, say, 2x, and I asked you what function was that the derivative of? Everybody would say x squared, because you've had enough experience with derivatives to know that. And that's the concept of antiderivative. So while 2x is the derivative of x squared is the antiderivative of 2x. There's a couple of issues here. The main one is that x squared isn't the only antiderivative of 2x, in that x squared plus 8, if I took the derivative of that, I would get 2x. X squared plus the square root of 7, that would be the antiderivative of 2x, because when I take the derivative of x squared plus the square root of 7, that would give me 2x. And essentially, x squared plus any constant, let's say c, when I take the derivative of this piece would give me 2x, and this would be 0. Therefore, the antiderivative of 2x could be this entire function. And so when we start talking about antiderivatives, we first have to talk about the basic concept of an antiderivative. And that's what this definition is talking about. So a function capital F is an antiderivative of this lowercase f function on some interval I if f prime of x equals f of x. And essentially saying that capital F is the antiderivative of lowercase f. So if I looked at that last example, lowercase f was 2x, capital F was x squared, let's say, plus some constant c. And so to check to see if this is in fact the antiderivative of this, we would take the derivative of f prime, capital F, and get capital F prime, which would be 2x, and we would get our f of x. So pretty simple concept of, what is an antiderivative. We're just going to do what we've been doing backwards. So now we need to tackle that concept of the plus c that I was just talking about a second ago. So the idea is that in that last example, x squared plus 8, x squared plus square root of 7, x squared minus 1002, these would all have been antiderivatives of 2x. And so the idea is the way we generalize all these is that each one of these has a constant added onto it. So we'd say x squared plus c is the antiderivative of 2x. And so we call this the family of antiderivatives. So this idea that, yeah, f of x itself is the function piece of this in terms of having the x value in there, but the c added onto that is really the true antiderivative, and we call this the family of antiderivatives, or the general antiderivatives, where the c is what we call the constant of integration. And so when we do any of these things and finding the antiderivative, rather than write each specific one, because we could do this forever, any constant I put here, here, or here will actually work. We just say x squared plus c, where c could be any constant. And this is, again, what we call the family of antiderivatives, where c is the constant of integration. So now we need to come up with some sort of notation for antiderivatives. All right, first off, the process of finding an antiderivative we call antidifferentiation, okay? Or we also call it an indefinite integral or indefinite integration. The symbol we use to denote this is this symbol right here. This is what we call the indefinite integral symbol. And a lot of this stems from the concept of differentiation. So we have this notation here that you're used to, dy dx equals some function, okay? So we took the derivative of some function, dy dx represents the derivative of that function, and that's equal to this random f of x function, okay? We could take that notation. What I can do is I could take this dy dx, and I can bring it over to the other side of this equation. So now I just have dy equals f of x dx, okay? What did dx stand for when we were doing the derivative? The dx stood for the variable we were taking the derivative with respect to. So, remember dy dx. dy was the derivative of y, and dx was with respect to x. So when I switch this dx to the other side, remember that's what that dx stood for. Okay, so now what I'm going to do is I'm going to take this equation here, and I'm going to apply this integral symbol to both sides. Okay? So this is the same equation. I applied the integral symbol to both sides. Well, this integral symbol means find the antiderivative. So if you think about it, on this side of the equation here, if I do the antiderivative of dy, dy was the derivative of y. What you're basically asking yourself right here is, the derivative of y is the derivative of what? And so because that's what this is, right? You're trying to say, what is this the derivative of? That's what this symbol means. So this is the derivative of y. So ultimately what that will give us would be y. And so then what we have to do is say, okay, then let's apply this over here to this one. So if this antiderivative symbol, we're saying let's find the antiderivative of f. Well, we already said this capital F of x plus c is the antiderivative of f. So again, this antiderivative notation is this integral symbol. When I apply that to some function f of x with respect to x, it's going to give me the antiderivative plus c. And that's the original function that I took the derivative of. Quick way to check your answer when it comes to this is that I could just take the derivative of this antiderivative here, and I should get back to the original function. Okay, pretty simple. So we have some basic differentiation rules that we've looked at previously. And so the idea of integration is to go backwards. Antidifferentiation is to go backwards. And so some rules are very easy to go backwards from. So here's a list of some really simple ones to go backwards from. And so first, let's say we have the derivative of a constant. We know that the derivative of a constant is 0. So then if I start with 0 and I take the integral of 0, I should get back to a constant. We know that the derivative of some constant times x should be that constant k. So if I then take the antiderivative of some constant with respect to x, I should get kx plus c. And so the idea with all these is we're going to start here and we're going to go back to that. If you look at this next one, this was the constant multiple rule. So we knew that the constant multiple could get pulled outside of the derivative. And then we could just take the derivative of the function itself. Well, if I'm going to do this with integration, it should really work the same way, because then I would just work with this function and multiply the constant back in again. So essentially I could pull the constant multiple outside of integrals as well. Sum and difference rule, we could take the derivative of this one and the derivative of this one separately and then add them together. Well, that should work the same way with integrals. I take the integral of each one separately, then add them together, as long as it's with respect to the same variable, x, in both cases. Power rule, if you look at your power rule, you would take the derivative of the power rule, you would bring that power out to the front, the new power is 1 less. But we have to reverse that. We have to kind of work our way backwards. So now if we're starting with x to a power, we have to add 1 to the power. And instead of bringing that power out to the front, we have to divide by that new power. In which case, this actually undoes what we did over here. And so this is our new power rule for integration, where we add 1 to the power and divide by the new power, then plus c. Notice, n can't be equal to -1. If n was equal to -1 here, then this would be -1 plus 1, -1 plus 1. And you would have x to the 0 over 0, which you can't happen. So this power rule for integration applies as long as n doesn't equal -1. If n is -1, that would be the same thing as talking about the integral of 1 over x dx, which we're going to mention down here in a second. Probably one of the easiest ones here is that we know that the derivative of e to the x is e to the x. So then if we go backwards, the integral of e to the x would also be e to the x plus c on all these, obviously. And then the last one, you know the derivative of your log is 1 over x. So now here's where we take the integral of 1 over x. This is the same thing as x to the negative 1. This is not a power rule situation. As long as x is not negative 1, we could use this power rule. But in this case, we can't because we saw we would get x to the 0 over 0, which doesn't make any sense. That's because this one, if we go backwards from the derivative rule, would give us the logarithm, plus c on the end, as with all of them. The best thing for us to do is to see these things in action. So let's look at this first one, the integral of 3x dx. Well, the 3 is a constant multiple which can be pulled out. So I'm really just taking the integral of x dx. Now that's x to the first power. So that's a power rule problem. So we saw that what we should do is in order to integrate x to a power, as long as that power is not negative 1, which it isn't, we should add 1 to the power and then divide by whatever that new power is, throw plus c on the end, which ultimately gives us this 3, again, constant multiples just sitting out there, 3x squared over 2 plus c. Now, if you have questions of whether or not this is going to work, remember, now you can check to see if this is in fact the antiderivative of this function by taking the derivative of this. If you took the derivative of this, what would you do? You take the power, pull it out to the front, and subtract 1 from the power. Well, if that power comes out to the front, it would cancel with this 2, and the new power will be 1. So I'd still have the 3 there, and I have x to the first, which is exactly what this is. So you see, it works. Next one, similar to things we did with differentiation, I'm going to rewrite this. I'm going to rewrite this as x to the negative 3 dx. Because the power rule doesn't apply to 1 over x to a power, it only applies specifically to x to a power. In this case now, looking at this x to the negative 3, I could apply the power rule to it. As long as the power is not negative 1, it's not. It's negative 3. I can say this will be x to the negative 3 plus 1 over negative 3 plus 1 plus c, which would give me x to the negative 2 over negative 2 plus c. Best way to write this would be negative 1 over 2x squared plus c. Final one, I'll rewrite it as x to the 1/2. Again, another power rule. If I take the antiderivative, I have to add 1 to the power and divide by that new power. So what you see here is we end up with x to the 3/2 divided by 3/2 plus c. If we're dividing by a fraction, we need to remember to flip and multiply, so it's actually times 2/3. And there's your answer. Here's another one. This one is usually one that gives people some trouble, but think about this. They go, well, what am I supposed to integrate? There can always be a 1 here, so 1 dx. So you ask yourself, what did I take the derivative of to get 1? Well, x, right? The derivative of x is 1. Throw plus c on the end, and there's your answer. Integral of x plus 2. This is added, so I use the sum and difference rules. Derivative integral of x plus 2. Integral of 2 dx. So here you're going to get x squared over 2 plus 2x plus c. And you see that's going to definitely work. If you're not sure, take the derivative of this and you'll get back to x plus 2. So we basically have a very easy way of working with polynomials here. So if I look at this next one, I can do the integral of 3x to the 4th minus the integral of 5x squared dx dx plus the integral of x dx. They're all with respect to x. And so the 3 can come out. So I really just have x to the 4th dx. Minus the 5 can come out. I have x squared dx. And then I have x dx. What I have here are basically 3 power rule problems. So I end up with 3x to the 5th over 5 minus 5x to the 3rd over 3 plus x squared over 2 plus c. And there's my antiderivative. Again, not sure. Take the derivative of this. Here's a couple more. They're getting a little bit harder now. Notice that when we went through those basic rules for integration, where we were just reversing some of those derivative rules, there was no product or quotient rule that we reversed. Because thinking about trying to reverse the product rule or the quotient rule, that would be fairly difficult to do in working the derivative rule of a product rule or quotient rule backwards. So when it comes to these antiderivatives, these indefinite integrals, there is no product rule or quotient rule. So here I have to integrate a quotient. How am I going to do it? Well, what I'm going to do is not actually integrate a quotient. I'm going to rewrite this function a little bit. So first thing I'm going to do is write this as x plus 1 over x to the 1/2 dx. Then I'm going to do a trick that we've used for derivatives as well, where I'm going to say x over x to the 1/2 plus 1 over x to the 1/2. Split that numerator apart. Then I'm going to simplify each fraction. So x over x to the 1/2 is x to the 1/2. And this one I'm going to bring up and write this as x to the minus 1/2. And now what you have are two things added together, so I can integrate each one of these separately, and they're both power rule problems. So what do I end up with? I end up with x to the 3/2 divided by 3/2 means multiplied by 2/3, plus this will be x to the 1/2 divided by 1/2 means multiplied by 2, plus c. There's my answer. You go to the next one. Don't think that this is a power rule, which would be the most common mistake. I could pull the 2 out. A lot of people go, okay, x to the -1. Bring it up like we've done with the previous ones. But then the problem is they go, okay, let's do power rule. But you see, this is the one where you can't do power rule. So you go, okay, well, how am I going to do this? But remember, x to the -1, 1 over x, they're the same thing. And you're asking yourself, what is this the derivative of? Well, we know that that's the derivative of a logarithm. So the answer for this is 2 natural log of x plus c. Now, there's two ways to write that. You can write it as 2 natural log of x plus c, but you can also write 2 natural log of absolute value of x. Because remember, what we saw was that the derivative of log x, as well as the derivative of natural log of absolute value of x, both equaled 1 over x. And so, if I'm going backwards, I can go backwards to either of these. Now, if we go with this one, this is a little bit more of a stronger function in that this function contains this function plus more. So in this case, while if you didn't put the absolute value on this, you would be correct, putting the absolute value is a little bit of a stronger answer. Let's do another one. So I'm going to rewrite this one as the integral of 3x squared dx minus the integral of 7e to the x dx. The better you get at this, the less of these steps you write out, but at first we're going to write all these out. The 3 is going to come out. I just have x squared dx. The 7 is going to come out. I just have e to the x dx. And so this is a power rule, and this is an exponential one. So I get 3x cubed over 3 minus 7e to the x. Integral of e to the x is e to the x because the derivative of e to the x is e to the x. I can cancel these two 3's, and so I get x cubed minus 7e to the x plus c as my antiderivative.